Pure solid will have a high, sharp melting point. Sharp. That means they will melt at an exact temperature. Then you are asked to identify what your unknown was. Then what did you do? You added the known one to your unknown and you looked at the melting point. If your melting point was sharp, it means that unknown is that compound. If your melting point went into a range, it's not. That's contamination. So what does contamination do? They actually give you a range in the melting point. We are going to use that idea here to draw the phase diagram. So A is pure, B is pure. You get a sharp melting point here for B and a sharp melting point for A. Then you will mix A and B together in different ratio, and then in the lab you are going to heat that right above the melting point, which means at this point everything is in liquid form. Then you try to bring the temperature down slowly. As soon as it comes to the crystallization point, what will happen? How will you know the first crystallization has started? In your manual it's written that you look for the first crystal. I've changed that because I don't believe your eyes. So you'll be looking here, then you'll be looking in the other one. Whatever. Even if you don't see it, we'll say here. This is what we are going to do. In a test tube, right? In a test tube, you will have the mixture, and instead of putting in a thermometer, you will put a thermocouple, which is connected to a digital meter. What you will do is that using a tongs, you will put it into a water bath so that everything inside melts, liquid. After that, you take it out and place it above in the air. Then you monitor the temperature of your solution every 30 seconds. Right? Every 30 seconds. As soon as, say for example, we are along this one, as soon as your temperature comes to T1, what should happen to the recording of your temperature? It will become constant, a little bit constant. Why? Because your sample has started to crystallize. Crystallization is exosemic or endosemic? Exo or endo? Crystallization, exo or endo? Exo, which means the sample is giving off heat. So when the sample is giving off heat, then your temperature after going down then will become a little bit constant till everything has crystallized, which means from here it will become constant coming down, and then boom. From here, when everything is crystallized, it will go down. Unfortunately, this temperature will be closer to the room temperature. That's when you move into that air conditioning room. We'll ask them to reduce the temperature a little bit so that the air conditioning room will be below the room temperature. So what you will see is that after you plot the graph, this is what you should see. See that? A decrease, and then from here to here it will become slanting. Why? Because during this process the crystals are giving off heat till it comes to this point and becomes constant. Clear? So we won't be doing all the test tubes. One pair will be doing one or maybe one or two, or one will go by benches wise, we'll see how many of them. So what you will do, you will need to record the initial temperature and the final temperature. For pure one, it's only one. No initial, no final, sharp. Here, initial at 230, final at 144. Here, initial at 170, 144. Can you see the final one is all same? Then once that is done, you should be able to get a graph, something like this. Right? And this is your initial. Can you see when I have a point here, there is no point there. This one, initial, final, initial, final. We won't know this. Initial, final, initial, final, initial, final, just one. Once that is done, then you will need to plot a graph. And from the graph, you are expected to find what is the common point here along this line, which is known as the eutectic composition, eutectic temperature. And this is called eutectic point. So what does it mean? Can you see? Pure, sharp, pure, sharp, mixture, sharp. We can make this mixture behave like a pure compound. Where do we use it? You know, when you go into a building, when they have fire sprinklers, the fire sprinkler is actually blocked with one of these metals, which has got very low melting point. Even though it has properties of a metal which is hard, doesn't allow the water to drip out, but the melting point is very low. That's why as soon as there is a fire, that part melts, and the sprinkler goes on. Where else do we use eutectic composition in life? Understood this graph? Now, what does it mean? Above this mark, everything is? Which phase? This place, everything is in liquid form. This, along this line, crystals start to form. This region, crystals of B, which is CD plus liquid of Bi. Along this line, everything crystallizes. This region, all solid. This part, all liquid. Along this line, depending on the composition, we have a solid liquid. Here, it's a solid liquid, solid liquid. Here, everything is solid. So, all liquid, B plus liquid A, or it could be B plus liquid, because we don't know whether all of A is liquid here or part of the B is also liquid. So that's why we say solid B plus liquid. This side it will be solid A plus liquid. Here everything becomes solid. My interest is, at this point, what fraction of that solid liquid is liquid and what fraction is solid? You know, at this point here, or at this point here. How would I know? Because along this region here, this part, you got solid and liquid both. What fraction is liquid and what fraction is solid? We use the lever rule. L-E-V-E-R, lever rule. How do you do it? Very simple. You measure the distance from here and here. Right? O If you are at this point, then measure the distance from here to here, which is C plus D. If you are here, then it is A plus B. That's the total distance. Right? At this point, the distance from this point to here is
B.
and from here to there is B represents the solid part, A represents the liquid part. A over A plus B times 100 over 1 will be the percentage of
A.
liquid. Distance B over distance A plus B times 100 over 1 will give me the percentage of.
Solid.
That's the simplest I can explain. I can't go any below that. Understood? A, that means from that point towards the axis is liquid. From the point this side is solid. So today I have managed to explain to you the liquid phase diagram, that is UCST and LCST.
Yeah.
Then this one. Then I explained to you the lever rule and also what you have to do in the lab. Tomorrow you will get the graph. I sent an email to all the Tuesday group. We'll start at 9 tomorrow, okay? I have an appointment at 8, so I won't be able to come in at 8, but we should be able to finish the lab before 2 hours. Okay? So the lever rule that I have just explained. By the way, as I have indicated in this diagram here, you should be able to explain what happens this way and what happens that way. And the lever rule that I have applied here is basically looking at, say this is one phase diagram. I want to know what fraction of it is alpha and what fraction is the liquid. So I draw one line from there and find the distance from here to here and distance from here to here. So this over the total will be liquid, this over the total will be alpha. Okay? You see that? So from this point to this point it is 34.5 minus 5.2 to get this. Then I will have to find the distance from here to here and distance from there to there. So from here to here is liquid, from here to here is solid. This is engineering. Eh? If you were doing chemical engineering, then this is the kind of diagram you would have been studying. If you ask people who are doing engineering, they will tell you the lever rule, they will talk to you about the phase diagram. And remember, the reason we can't give you chemical engineering in this university is probably the caliber of students. As I said, in engineering, see, in science, if you do medical, you look after the sickness of people, right? When you do biology, then you go into two areas, animal side or plant side. When you come to do chemistry, we basically teach you three areas: physical, organic and inorganic. That is how matter basically behaves in nature. The role of an engineer is to understand how this matter behaves and put it into an application. And the moment you find that application, you become an engineer because you will design something from your chemistry. So that is why you will see in this course, you will see most of the things that I try to explain is in application to real life problem. That is, this part could be done this way. This part could be used this way. And that's what chemical engineering is. So when you get your chemical engineering degree, you come in, you join one in manufacturing plant, they will tell you to find a condition under which you will get maximum yield. Clear? And places where you get work is like the beverage industry here, Paradise Beverage, where they make beer. Then you do the process, then you go and check quality good or not. Same thing with Coca-Cola. If you prepare, you need to see how things are happening, what is the condition, what should be the pressure of the gas being filled in the bottle, whether the bottle will explode or not. So, that brings to the end of the topic. Now the next one will be systems of variable composition, and I will just go over